Hi, welcome to Math 113. This is class 4, Thursday, February 13th. We're going to cover sections 1.3 and 1.4 today. A couple of announcements before we get started. Your first homework on 1.1 and 1.2 is due this Friday. Your second homework assignment on 1.3 and 1.4 is due on Monday. And then your first exam is coming up on Thursday the 6th. So still a few weeks before that, and we'll talk about that many times before it comes. I just want to put it on your radar today. For two non-negative numbers, A and B, we write A and then this symbol, which you read as is less than B, if A is less than B. And we write A and then this symbol that was just the original one turned around. We read that A is greater than B if A is greater than B. These statements are called inequalities. Think of the less than and the greater than symbols as an alligator. It will always eat the bigger number. So for example, 8 and 5, 8 is the bigger number, so we put the alligator eating the 8. So this says 8 is greater than 5. So we want to put the correct symbol between each of the two numbers. Which number is bigger, 584,397 or 600,214? So we start by comparing the largest place value, okay? Because the largest place value in both of these numbers is the hundred thousands. And if you have more hundred thousands, if one number has more hundred thousands, then it's definitely going to be bigger. So 600,000 is bigger than 584,000. Okay. And then 7,587 compared to 13,098. So we want to compare the largest place value, and if they don't have the same number of digits, your two numbers, we can put a 0 here because there are 0 10,000s in this first number here. There's 7,000, 0 10,000s, 0 100,000s. And then this number, it has 3,000s, but it has 1 10,000. So this number has a 1, this number has a 0. So we're going to say the 13,000 number is bigger. So to summarize, we compare the digits in the leftmost place value that at least one of the numbers has a non-zero digit in. And what do we do if there's a tie in the leftmost place value? So for example, the leftmost place value of each of these numbers is a 9. Okay, they both have something in the ones place. It's a 9. So this is a tie, so how do I decide which number is bigger? We go to the place value 1 to the right. So in this case, they're both 5s. Okay, so we had the 9s were the same, the 5s are the same, so I move one more digit to the right and I compare the 3 to the 4. The 4 is bigger, so 9.54 is bigger than 9.5378. So to summarize, if there's a tie in the leftmost place value, move to the next smallest place value and compare. Each time there's a tie, move another place value to the right until the digits don't match. Okay, so next you're going to work on an activity. If you're watching this in a video and not actively in class doing this, I suggest pausing the video now, work on this activity, and then press play when you're done. Okay, so for each of the following pairs of amounts, determine which is greater and explain your reasoning. So 4 hundreds, 18 tens, which is unconventional. Normally we wouldn't write more than 9 tens, because once you have 10 tens, you have 100, right? So we have 4 hundreds, 18 tens, and 3 ones. So this is an unconventional way of writing this number. We can't just write 4, 18, 3, like if that said 8 tens, I could say, oh, that's 483. But because it's 18 tens, I have to be a little bit more careful, and I'm going to trade 10 of my tens to make another 100. Okay, so this is 5 hundreds, 8 tens, and 3 ones, which is 583. And then I have 5 hundreds, 7 tens, and 9 ones. No trading necessary. I can just write this as 579. Okay, so then I know that this first number is bigger, despite the fact that if you just compare the hundreds, if you didn't look in the tens at what they were describing for tens, you might think that this number is bigger because 500s is bigger than 400s. But because they didn't use the convention that we're used to, we had to account for the fact that there were an extra 10 tens in the tens and make it another 100. Okay, B, 1,000, which is 1 with 3 zeros. Okay. And then 743 tens. So 43 tens, every time you get 10 tens, that's another 100. So I have 4 sets of 10 tens here, and then I'll have 3 left over. So I have an additional 400. So I have 700 plus 400 plus 30 because of my 3 tens. 3 tens makes 30. 40 tens makes 400. Okay. So every time you get a set of 10 tens, we trade up to make it a bundle and trade it up to 100. So I have 400s. So that comes out to 1,130. So the second number is bigger. So again, this was a little bit tricky. It was kind of misleading because you might immediately think that 1,000 is bigger than 700, but we didn't account for the 43 tens. Okay, so we had to do some trading to figure out how many hundreds we had. Okay, part C, 2 ones and 4 tenths. So that's 2.1. And then 1 and 15 tenths. Okay, well, every time you have 10 tenths, that makes a 1. So I can take 10 of these and make a whole 1. So this is 1 plus 10 tenths plus 5 tenths. Okay, so that is 1 plus 1 plus 0.5 or 2.5. So the second number is bigger. Okay, 6 tenths, which is 0.6, and 42 hundredths. So 42 hundredths we can write as 0.42. Okay, 42 hundredths. That's the convention for how we say this number out loud. The last place value where we have a digit is the hundredths. So 42 hundredths, because 40 hundredths makes a tenth. So I have 4 tenths, and then I have 2 hundredths. 6 tenths or 83 hundredths. Well, 6 tenths is 0.6. 83 hundredths is 0.83. Okay, so 83 hundredths, that's 80 hundredths plus 3 hundredths, and 80 hundredths is the same as 8 tenths. So 8 tenths, 3 hundredths. Okay, so I didn't circle the biggest one in both of these. So this case, 6 tenths was bigger, and in this case, 83 hundredths was bigger. All right, why can we determine that 723 is greater than 699 just by comparing the 7 and the 6 and the hundreds place? Even though in part 1A, it was not correct to just compare the 400s with the 500s. So in a base 10 system, you will never have more than 9 in the next digit, right? No digit could ever have anything other than 0 through 9 in it. No place value could have anything other than 0 through 9. So if you have 700 here and 600 over here, there's no way that the remaining digits could give you another 100, could add up to another 100. Because if you had another 100 in a base 10 system, we would have automatically traded it and made this a 7. Okay, so because convention in base 10 says that as soon as you have a bundle of 10, you trade it and move up a place value. So there's no way there could be another 100 hiding in the tens place. You would have to have 10 tens, and we would never write 10 in the tens place or anything bigger. It would have to be a 0 through a 9. Okay, so tenths are greater than hundredths. 1/10 is greater than 9/100, but is 1/10 always greater than any number of hundredths? No, because if you have more than 10 or more hundredths, you have a tenth or more, right? Because 10 hundredths equals 1/10, right? So 10 hundredths would be written like this, and that equals 1/10, okay? And any number of hundredths larger than 10 is going to be more than 1/10. So say 75 hundredths would be greater than 1/10 because it is 0.75, which is greater than 0.1. Okay, we have one interesting exception to the place value method that we use to compare numbers. Let's analyze these sets of numbers and see which one's bigger, 1 or 0.9, 1.0 or 0.9. So the leftmost place value in the number on the left is a 1, and in the number on the right is a 0, so 1's going to be bigger. Okay. How about 1.0 and 0.99? So 1 compared to 0, 1 is bigger. 1.0 to 0.999. So the 1 compared to the 0, the 1 is bigger. So you can see 1 seems to be bigger. No matter how many 9s we add on to the end here, 1 is bigger. But 1 compared to 0.999 repeating forever. Forever, okay? Which one is bigger? So our convention would say, look at the 1, look at the 0, the 1's got to be bigger. Okay, but it turns out that these are actually equal. And I'll do an explanation of why on the next slide. So why is it that 0.999 repeating forever? You can never stop writing 9s. Anytime you stop writing 9s, that 0.999999999 will be smaller than 1. But if you repeat forever to infinity, it equals 1, okay? So 2 ways we can think about this. One is to ask yourself how much bigger 1 is than 0.999999999. Like if you tried to subtract them. 1 minus 0.999999999, repeating forever, right? The answer would be, you're repeating forever, the answer would be 0.0000000. You keep putting down zeros forever, right? And eventually, when you stop writing 9s, you'd put a 1. But because we never stop writing 9s, I just keep writing 0.0000 ... right? So the difference between the two numbers is 0, which means they have to be the same. Okay, so another way we can think about this is most people have seen, like on a calculator or by doing long division, that 1/3 is equal to 0.3 repeating forever, right? Okay, so we'll see this when we cover division later in the semester, but this statement is true. Okay, and then if I were to multiply both sides of this equation by 3, okay, so 3 times 1/3 is 1, and 0.3 repeating times 3 is 0.9 repeating. So they do end up being equal. Okay, comparing negative numbers. We're going to put the correct symbol between each of the two numbers, -5 and -3. So you can think of this as money in a bank account. So for example, if one person has -$5 in their bank account and another person has a balance of -$3, who has more money? The person whose balance is -3 has more money because they owe less money. You can also think of this in terms of degrees Fahrenheit, which is warmer, -5 degrees or -3 degrees. Okay, so -5 is colder than -3. -3 would be warmer, so -3 is the bigger number. On a number line, numbers to the right are always greater than numbers to the left. So for the -5 and -3 example, here's -5, here's -3. Negative 5 is to the left of negative 3, so it is less than negative 3. Here's another activity. If you were watching this as a video, please pause, attempt the activity now, and when you're done, you can press play to see me go over it. Okay, so we want to explain in 2 different ways why a negative number is always less than a positive number. So a number line would be a good way. Number line, because negatives are to the left of positives. Okay, we could also talk about money in a bank account or temperature, right? Negative temperature will always be colder than a positive temperature. Okay, a student might not think that negative 5 is bigger, or a student might think that negative 5 is bigger than negative 2. So I want to describe 2 different ways to explain this. So again, a number line will show that negative 5 is to the left of negative 2, making it smaller. Negative 5 is less than negative 2 because negative 5 is to the left of negative 2 on a number line. Or we could talk about temperatures or money. So for each of the following pairs of numbers, write an inequality to show how the numbers compare. So negative 6 compared to negative 5.9. I'm going to make a number line, and it may be helpful to put the positive counterparts on here first. So here's 0, 1, 2, 3, 4, 5, 6. Okay, so here's 6. 5.9 is going to be a little bit before it. Okay. And then I'm going to do the opposites. 1, 2, 3, 4, 5, 6. So here's negative 6. And negative 5.9 is a little bit before it. Okay. So when I'm comparing negative 6 and negative 5.9, negative 6 is going to be to the left of negative 5.9. So negative 6 is smaller. And then I can draw a similar number line for the next example. So I've drawn a number line, I put 0 on it, and then this is not to scale, I just put 4.7, 4.8, and then I drew their opposites, negative 4.7 and negative 4.8. So negative 4.8, well, let's do positive. So here's positive 4.8, and 4.777 is like, I don't know, 3/4 of the way to 4.8. And we don't have to be perfect about where that location is. I know that it's somewhere between 4.7 and 4.8, closer to 4.8. Okay, so I just put a dot there. And then I'm going to draw the opposites of these 2 numbers over here. So I have the negatives. So here's my negative 4.8, and here's my negative 4.777. So my negative 4.777 is to the right of negative 4.8, so it is bigger. For this last example, I've drawn another number line. I put positive 0.1 on it, and I went up by tenths. Okay, so I'm going to plot these 2 numbers, 0.1 and 0.555, the positive versions. Okay, so here's 0.1, and here's 0.555. It's somewhere between 0.5 and 0.6. And then I'm going to put their opposites on the number line. So I have negative 0.1 and negative 0.555, it's about right there. So when I look at the 2 negatives, okay, the negative 0.555 is to the left of negative 0.1, so it is smaller. Okay, given this number line, we want to write inequalities to show how each pair of numbers compares. So I have the opposite of p plotted, which means I can put the opposite of p on here. Just kind of use some symmetry. P is going to be about right here. And I can put the opposite of R, so just the same distance, but on the other side of 0, so negative R. Okay, and now I have a number line with all of my R and P, negative R and negative P, and I can compare them. So negative r compared to negative p. Negative r is to the right of negative p, so it is bigger. And then for r and p, p is to the right of r, so p is bigger. Okay, so we've talked about comparing numbers. Now we're going to talk about rounding numbers. Okay, so to round a number, this is the general rule that you learn in elementary school. You first identify the place value which we wish to round to, and then we observe the digit in the next smallest place value. And if that digit is 5 or more, we add 1 to the digit in the higher place value. And if that digit is 4 or less, we leave the digit in the higher place value alone and put zeros in all the place values smaller than it. So for example, I want to round 3.74 to the nearest tenth. So I like to put a little underline under the place we're rounding to. And then once that's underlined, look it to the place to the right, the next smallest place value. That number is a 4. Okay, if this number is 5 or more, you round up. And if it's under 5, 4 or less, you round down. So we're going to round down to 3.7 here. And now I'm going to take 3.76 to the nearest tenth. So again, I'm going to underline the tenths place because that's where they told me to round to. Look one place to the right. That number is bigger than 5, so I'm going to round up. I'm going to bump up this 7 to an 8. And I round up to 3.8. One way that teachers can show this method of rounding is called the mountain method. So if I want to round 3.74 to the nearest tenth, I'm going to make a number line, and I'm going to put 3.7 on it, and I'm going to put 3.8 on it, okay? Because the tenths below to the nearest tenth is either going to be 3.7 or 3.8. Okay, so I put the two of those on there, and then I'm going to identify the point halfway between 3.7 and 3.8, which is 3.75. And I'm going to make a mountain. And then I'm going to plot the point 3.74, which is going to be a little bit to the left of 3.75. And put that point on the mountain. And because it's to the left of 3.75, that point is going to roll down to the 3.7. Okay. And then the 3.76, that's a little bit to the right of the midway point, 3.75. So that is going to roll down the mountain and land at 3.8. So let's use the mountain method to round 3,523 to the nearest hundred. Okay, so the hundreds place is right there, underlined. It's got a 5 in it. So the nearest hundred is either going to be 3,500 or 3,600. So I'm going to draw a number line. And I'm going to put 3,500 on it, and I'm going to put 3,600 on it, and I'm going to mark halfway in between, which is 3,550. And I'm going to draw a mountain. Okay, and then I'm going to identify 3,523. It's somewhere about right here. Okay. And so I put a point above it on the mountain. And because we are on the left side of 3,550, that point is going to roll down to 3,500. And now I'm going to round 3,550 to the nearest hundred. So nearest hundred is either going to be 3,500 or 3,600. 3,550 is the halfway point. And when you're at the halfway point, in real life, you could kind of go either way. And mathematicians and society as a whole has decided that when we hit exactly the halfway point, we're going to round up. Okay, so if you're right at the peak of the mountain, you go to the next 100, 3,600. Okay, we've come to another activity. Pause your video and take a few minutes to work through this, and then you can press play to see me go over it. Okay, so number 1, we want to round points A and B to the nearest 100. So they're both between 7,300 and 7,400. The halfway point visually looks like it's about right there, and that would be 7,350. Okay, so point A is going to round down. A is going to round to 7,300 because it's to the left of the halfway point, and point B is going to round up to 7,400 because it's to the right of the halfway point. So possible numbers that A and B might represent, okay, A could be anything smaller than 7,350, maybe 7,335. And B would be anything bigger than 7,350, maybe 7,375. Which numbers in the interval between 7,300 and 7,400 would round down to 7,300? Okay, well, let's mark the 7,350, the halfway point. These numbers round down, okay, not including the 7,350. Okay, so any number between 7,300 and 7,349, okay, including 7,300 and 7,349, those round down. Okay, and what do all those numbers have in common? They have a digit of 0, 1, 2, 3, or 4 in the tens place. Right? Because when you're rounding to the nearest hundred, you look to the tens place, and we have 0 here, and every number in this interval has a number in the tens place that would be a 0, a 1, a 2, a 3, or a 4. As soon as you put a 5 in that tens place, it's going to round up. Okay, so which numbers in that interval round up to 7,400? So again, I'm going to mark the halfway point, which is 7,350. And the numbers that round up would be from 7,350 to 7,400. Okay, so 7,350 would round up to 7,400. And what do those numbers have in common? They all have the digit in the tens place is 5 or bigger. Is 5, 6, 7, 8, or 9. So when we round a number to the nearest hundred, why do we look at the tens place? The digit in the tens place tells us whether we are to the left or the right of the halfway point between the two closest hundreds. Okay, we're going to skip this activity. We did not have time to do this in class, so skip. Feel free to work on it if you are interested, though. We also skipped this activity. And we didn't manage to cover these last two questions in class, but I'm going to do them here so that you have it for reference. It was reported that 25,000 undergrads are enrolled at UMass this semester. Assuming this number is rounded to the nearest 1,000, how many undergrads could this rounded number represent? So we were rounding to the nearest 1,000. Okay, so if I was on a number line, okay, 25,000. 26,000 or 24,000. Okay, so we rounded to 25,000. So we could have rounded up from some number over here, or we could have rounded down from some number over here. Okay, so these would be the halfway points. So this would be 24,500, and this would be 25,500. So the numbers in between here could round to 25,000. Okay. The 24,500 would round up, so I'm going to include that one. But the 25,500 would round up to 26,000. It would not round down to 25,000, so I'm not going to include the 25,500. So that means that there could be anywhere from 24,500 to 25,499. Okay. Anywhere in there could have rounded to 25,000 to the nearest thousand. A meteorite is said to weigh 8 kilograms. What range would the actual weight be between? Okay, so if it's reported as 8 with no decimal points, we're going to assume, we have to assume that they rounded to the nearest whole kilogram. Okay, so if I put a number line down, 8 is what we rounded to. Okay, so it probably would be, so it must be that it was somewhere between 7.5 and 8.5. Okay, and we are going to say including the 7.5. Okay, because 7.5 would round up to 8, but not the 8.5. Everything in between those would round to 8. Okay, so the meteorite might weigh anywhere from 7.5 to 8.4 kilograms. But what if the weight of the meteorite was reported as 8.00 kilograms? In this case, we're going to assume that they rounded to the nearest hundredth. By including those two decimal points, they are telling the reader that they rounded to the nearest hundredth. So when I make my number line and I put 8.00 on it as what I rounded to, okay, the next hundredth up would be 8.01. And the hundredth below would be 7.99. And then I need to mark the halfway points in between those. So this one would be 8.005, and this one would be 7.995. Okay, and it could be that the meteorite weighed anything from here to here, 7.995 to 8.005. We would include the 7.995 because that would round up to 8, but we're not going to include the 8.005, okay, because that would round up to 8.01, and we want only things that round down to 8. So it could weigh anywhere from 7.995 kilograms to 8.004 kilograms.